Okay, hello everyone. My name is Carter. This is 2008 Step 2, Question 4 on a theme of differentiation. Okay, so let's just go through the question and effectively summarize what's going on before we really get into it. Right, so we have a curve which is given by x squared plus y squared plus 2axy is equal to 1. So it's like an implicit function, effectively, right? It's not in the form it's not explicit. It's not in the form y is equal to um, f of x, right? Effectively, there's no like y is equal to then a bunch of stuff involving x. It's more sort of like the x's and y's are on one side, and you got like x squared and y squared and 2axy, and that all equals 1 when you add those things together. So it's not implicit. It actually ends up being sort of a rotated ellipse. And I'll leave that, I guess, as an exercise to the reader. No, I don't like to do that, but it's not really relevant to the question. It doesn't help you complete the question. And although I like to talk about extra things, I think I'll leave that. If you are interested, though, I might make like an extension video to this, maybe post on the channel if you are interested as to how we can show that that's a rotated ellipse. But it's kind of not important for the question. Okay, so a curve is implicitly defined by this function here. So x squared plus y squared plus 2axy is equal to 1, where a is a constant such that a is strictly between 0 and 1, non-inclusive, so it doesn't include 0 and 1. Show that the gradient of the curve at some point p with coordinates xy is given by this, so minus x plus ay all divided by ax plus y. So the first part of this question, I mean, effectively, all we plan to do here is just use implicit differentiation, right? So we have some effect. Let's me right. We have effectively we effectively have that x squared plus y squared add 2axy is equal to 1, so it's like an implicitly defined function. And so obviously you can differentiate both sides. So differentiating both sides. Let me just make sure also this can be seen. I don't want to be like writing in this. Okay. So differentiating both sides, we have. So obviously when you differentiate x squared, so obviously I should really say differentiating both sides with respect to x, obviously. We have that 2x, right? Because the derivative of x squared is 2x. Add the derivative of y squared, so that's going to be 2y dy dx. This is implicit differentiation, and y is a function of x. So we need to use our chain rule. And then we have this 2axy. So this is a actual product rule usage here. So we differentiate 2axy. That just gives us 2a. So we have that's plus 2ay. And then you differentiate the effectively the y. And that just gives you dy dx. So you're going to get 2ay, add 2ax, dy dx. Okay. And we have that this is equal to, so that's the entire left-hand side when I've taken the derivative of it with respect to x. Then I have 1. I take the derivative of that with respect to x. I get 0. Because the derivative of a constant is just 0. And now we can just move stuff to one side. So everything that doesn't have a dy dx in it, we move to the other side. So we just get 2y dy dx add 2ax dy dx is going to be equal to, this has to be right, is going to be equal to minus 2x minus 2ay. And then we can factor out a dy dx from the left-hand side. So this gives us dy dx multiplied by 2y plus 2ax is going to be equal to minus 2x minus 2ay. And then you can just divide both sides by 2y plus 2ax. So you're going to get dy dx is simply equal to minus 2x minus 2ay divided by 2y add 2ax. And actually that minus, sorry, should be up there, because otherwise you'll think it's minus bracket like this. But it's not. So the minus should be up here. So it's minus 2x minus 2ay divided by 2y plus 2ax. Divide everything by 2. You can get a common factor of 2 at the top and bottom. And this gives you minus x minus ay divided by y plus ax. And so if we go back up to the expression, is that the expression we wanted? We wanted minus x plus ay over ax plus y. So we do have ax plus y in the denominator. We can just take out a factor of minus 1 from the numerator and put that in the front, and then write it as minus x plus ay. So that's kind of like as if there's a bracket there, right? Because minus x minus ay is the same as minus in brackets x plus ay. And then that's all divided by y plus ax. So we have that dy dx is equal to minus x plus ay divided by y plus ax. And that's really what they were asking for here, right? They're saying show that the gradient of the curve. The gradient of the curve is just the derivative. Well, I mean, it's a curve in 2D, right? So effectively the gradient of that curve is going to be the derivative, since y is effectively a function of x, going to be dy dx, right? Saying how is y changing as your x changes, right? And so that's really whenever we say the gradient, really just mean the derivative with these types of problems, right? Effectively just like a tangent. What's the slope of the tangent at that specific point, x, y, and it's general. So we're looking here for the derivative dy dx. Okay. Right, and now we need to show that theta, the acute angle between OP and the normal to the curve at P, satisfies this requirement. Tan theta is equal to A mod y squared minus x squared. Okay, so effectively, you can think about this as sort of, one way I think is useful to think about this is sort of using vectors. A lot of people don't like vectors, but they are quite useful, I think, especially in this scenario here. So effectively, P is just a random point on the curve, right? I did say before it's a rotated ellipse, but you don't actually need to know that, right? You just treat OP as a vector, right? And it's a vector from the O, which is origin 0, 0, to the point P, just x, y on the curve, right? So OP, effectively, if I just go back down. So OP effectively is just a vector, right? So it's just a vector from sort of 0, 0 to some point on the curve, like just an arrow like that, right? And then effectively the normal to the curve at P. Well, we know what the tangent, so we know what the gradient of the curve at P is going to be. So the normal to the curve at P is effectively going to have is going to be a line, right? Since the sort of tangent at a curve is a line, the normal is perpendicular to that tangent, and that specific line is going to be, since it's perpendicular to the tangent, is going to be the negative reciprocal of this quantity here, right? The negative reciprocal of negative x plus ay divided by ax plus y. In other words, is going to be, so you can do -1 divided by that, so -1 divided by minus x plus ay divided by ax plus y. And obviously you see the minus signs cancel, and you end up just that flips the fraction. So you get ax plus y divided by x plus ay. So you can effectively write the normal as a vector, right? So you could write the normal, what do they call it? So the normal at P, so you could say normal vector, right? And we can write it in the following form, effectively, well, x plus ay, and then y plus 2a, sorry, y plus ax, right? Because effectively, if we go back up here, you can effectively see that this is effectively the gradient of our normal, right? This is just the gradient, and you can't actually see what I'm trying to say. This thing here is the gradient of our normal, and the gradient is kind of just like your rise over your run, right? Your rise over run. So effectively, if we just think about like the normal at some arbitrary point, it might look something like that. But like effectively, if you can compute the gradient as sort of the change in y, so delta y, and then divided by your change in x, your delta x, that's how the gradient works. And so effectively, we could treat our change in y as this. In this case, we could treat it as ax plus y, and we could treat our change in x as x plus ay, right? And so effectively, you can see that when we do our change in y divided by a change in x, we're going to get ax plus y divided by x plus ay, which is precisely the gradient of our normal, and is given is what we calculated here, right? So effectively, as x changes by this specific amount, x plus ay, the y value of our function will have to change, or of our normal, sorry, will have to change by this amount. It's just another way of sort of like writing the gradient of our normal line, but instead of writing it like sort of just as this fraction, we can actually represent it as a vector. We can represent, we can represent the normal line as a vector, and then effectively code the gradient into that vector. Okay, and obviously OP as well. We could write that effectively. You could write that that's just effectively a vector going from the normal to the point P. And so what we're effectively doing in this part of the question is we're finding the angle between these two vectors. So we're finding the angle between OP, right, and the normal to the curve at P. And so really all that we need to know is how do you actually find angles between vectors? Well, there's a couple sort of formulae that you might think are relevant, right? So for example, if I give you two vectors A and B and you dot them, then you should indeed know that A dot B is specifically equal to the mod of A multiplied by the mod of B multiplied by cosine of the angle in between the two vectors, right? So effectively, the dot product of two vectors is just equal to effectively their magnitudes multiplied together, and then you multiply that quantity here by the cosine of the angle in between the two vectors. So if they're like two vectors, are just like you can think of them as arbitrarily just arrows pointing with some direction. So obviously vectors have both direction and magnitude, so they're just arrows pointing in some direction with a magnitude. And so you have two of them. You can find an angle in between them, a little bit like this, like the angle here, and effectively that's the theta that we have here, right? So we can calculate the angle in between two vectors by considering this formula. And this formula I'm not going to prove, but it is one that I would expect that you probably should know, at least for step 2, step 3, maybe. And so it's just a useful formula, and you learn it as well in further math. So if you are doing that and you don't know about this, I would definitely have a look at it. Also, though, we do know something about the cross product of two vectors. So actually, the cross product of two vectors. So the vector A crossed with the vector B. Obviously, that actually gives you a vector as an output. So we have to take the magnitude of that vector. The magnitude of the cross product of two vectors is actually precisely going to be the mod of the first vector. So like the magnitude of the first vector multiplied again by the magnitude of the second vector, this time multiplied by sine of theta. Theta is the exact same here as it was above. It's just the angle in between the two vectors. And so what we actually notice is that tan of the angle, so tan theta, and by the way, this theta is exactly effectively what we're trying to calculate, the angle in between our OP and our normal vector. So tan theta, we can effectively see, is just going to be this thing divided by this thing, because the magnitude quantities are just going to cancel out, right? And clearly none of the vectors that we're considering here will have zero magnitude, otherwise it just effectively be a point. So that's irrelevant, we're not going to be dividing by zero. And so we clearly therefore have that tan theta is simply equal to the magnitude of the vector A crossed with the vector B divided by the vector A dotted with the vector B. And that's actually a useful formula effectively to have. But as well as that, though, well, this is useful, but it's not too useful until we actually know like what actually is the vector A dotted with the vector B. Well, let's just consider the vector A effectively have components A1, A2, and the vector B is just another vector, and this vector has components B1, B2. Right. So whenever I dot these two vectors, effectively we know by definition that A dotted with B is going to be equal to A1, B1 add A2, B2. So we can effectively replace that dot A dot B on the bottom with this. So on the denominator there we have A1, B1 add a2. Sorry, that should say b2. But the cross product is a little bit sort of less known. But effectively, since we're doing the mod of the cross product, well, one way you can write the cross product of a vector of two vectors, sorry, is effectively if you have a vector A, and you cross it with a vector B, you can sort of write it in this form here. So you're going to have a2 b3 minus a3 b2. Because obviously, whenever you take just the cross product without taking the magnitude, you're going to get a vector back. And typically, we think about vectors as being, well, at least when we take cross products, we typically think about them in 3 dimensions. Except obviously, in this case, we're in 2 dimensions. So everything that has a 3 in it, so b3, for example, is going to be have a 0 component, right? So we could write these vectors a and b as 3-dimensional vectors with a 0 component because they have no z component, right? But for now, let's just treat them as 3-dimensional because this is just like the formula that you get from that. So you have a2 b3 minus a3 b2 multiplied by that sort of I hat, the unit vector in the x direction, add a3 b1 minus a1 b3 multiplied by j hat, so that's like the unit vector in the sort of y direction, and then add, so one more thing, and then add a1 b2 minus a2 b1 in the sort of k or in the z direction, right? Well, we know that all of these things here, these are just 0, right? Because we're in the xy plane, so we could treat a and b as 3D vectors with 0 components for their for 0 as their z components. So this all becomes 0, right? This is 0, 0, 0 minus 0, 0, 0 multiplied by anything is 0. This is all 0, 0. And then all we have left is a1, b2 minus a2, b1, right? Multiplied by k hat, so in the z direction. But that actually doesn't matter because obviously when you take the magnitude, right? Whenever you take the magnitude of these two vectors crossed together, well, you can see this is just going to be the square root, right? Because it's just like a vector pointing straight up in the sort of z direction, right? And so it's just going to be the square root of a1 b2 minus a2 b1 all squared, and the square root and the squared cancel out. And effectively, you just get, well, the square root of anything squared is just simply going to be the mod of that thing. So you just get simply the mod of a1 b2 minus a2 b1, right? So effectively, the mod of a cross b is, we could rewrite it as this: the mod of a1 b2 minus a2 b1. And so we go back up and we like fill that space in. So here we have the mod of a cross b simply is equal to the mod of a1 b2 minus a2 b1 as so. Okay. Well, what we also know effectively is well, we can just write this OP here as a coordinate, right? Because it effectively is just like a position vector, the sort of vector OP. We can just write it as xy because we know that since it's going from the origin to the point xy, the gradient is simply going to be, this is just our point xy. The gradient is simply going to be y divided by x, right? So we know the gradient of that sort of OP, and we also know the gradient of our normal, which is given by y plus ax divided by x plus ay. But now that we have these two sort of vectors, we can just basically plug into our tan theta formula different components, right? This is effectively like our vector, we call it a prime, right? This is our sort of like a prime vector, and this is like our b prime vector here, right? And so then when we plug these into our sort of formula, so a1 prime b2 prime minus a2 prime b1 prime, we can just basically calculate that. And so what you're going to get when you do that is you're going to get mod x multiplied by y plus ax, right? Minus y multiplied by x plus ay on the top, and then on the bottom, we're going to get u dot v, so it's going to be what? a1 b2, a1 b1 and a2 b2. So that's effectively just going to be x multiplied by, oh sorry, you guys can't even see it, god dang. Didn't even notice that. Okay, I need to be a bit more active on my moving the page. Anyway, on the denominator we have x multiplied by x plus ay, right? Add y multiplied by y plus ax. So we can effectively just clean up everything that we have on the top there, and that's just going to give us so xy add ax squared minus yx minus ay squared. So this xy and the yx, they actually cancel, right? And that's it in the mod. And on the bottom, well, what do we get on the bottom? Well, we're going to get x squared add axy add y squared add axy. Okay, so that's just going to give us effectively x squared add axy add y squared add axy. Okay, and so you can see that that's x squared add y squared add 2axy. So effectively on the top, what we get is the mod of a multiplied by x squared minus y squared, right? And then on the bottom, well, we just get x squared add y squared add 2axy. Okay, well, clearly the equation of our curve, effectively the implicitly defined function that we started off with, tells us that x squared plus y squared plus 2axy is actually equal to 1. Okay, that has to be true, specifically because we're treating xy as points on this curve, right? So we're treating y as points that effectively lie on this curve. And so for that reason, the sort of point xy must satisfy this sort of equation here: x squared plus y squared plus 2axy is equal to 1. And so we actually know, right? We actually know that that this thing here, this x squared plus y squared plus 2axy, is just going to be equal to 1. So this just gives us the mod of a multiplied by x squared minus y squared divided by 1. Okay, so that's pretty interesting. So that just gives us that. And remember, this is all equal to tan theta, right? is equal to tan theta. And so therefore what we have, so tan of theta is therefore equal to the mod of a multiplied by x squared minus y squared. And we're also told that a is between 0 and 1, okay, not including. So a is positive, so we can just take it out of the mod, right? Because it doesn't matter. So a is just equal to a mod x squared minus y squared. And what exactly were we looking for? We're looking for, you just show that tan theta is equal to a mod y squared minus x squared. So that's obviously an easy fix, because effectively the mod of y squared minus x squared, the mod of x squared minus y squared is equal to the mod of y squared minus x squared. And that simply just follows because the mod of x is equal to the mod of minus x, right? That's just a property of the modulus, right? So if you plug in a negative number into the modulus, you're going to get the same output as if you plug in the positive representation of that number. And that's just all you're doing here. You're multiplying the inside by -1. So you're not really changing the output of the mod. You're just changing the thing you input. It doesn't matter because it gives you the same output. This is actually equal to a mod y squared minus x squared. So tan theta, where theta is the acute angle made between effectively those two vectors, is just going to be equal to a mod y squared minus x squared, exactly as we required. Okay, so we've done that. I think that's probably the hardest part of the question, to be honest with you. It takes you can also think about it by thinking about slopes effectively, and then using the tan angle addition formulae, which is the way I think I went about it for the first time. Like effectively, you can just bring the lines to the origin, and then you have an angle made with each line to the origin, and then you just do tan of a minus b, and you use that formula. That also works, but I actually thought this would be quite elegant as a solution, so I thought I'd talk about this method instead. Anyway, so we have shown further that if d theta dx is equal to 0 at this point p, then these following conditions hold. So this is going to be just sort of, we need to sort of connect the puzzle pieces here. So we have lots of information that we already have up here. We need to use it for some stuff to prove down here. So how exactly then are we going to be able to do this? Well, one way that we can do this effectively is just by considering, or just by implicitly differentiating this sort of equation here. This tan theta is equal to a mod y squared minus x squared. And let's just go ahead down here. I just move the page down. Let's just go ahead and do that. So obviously what we have is we have that tan of theta is equal to, let me just move this over here, tan of theta is equal to a mod y squared minus x squared, right? And effectively, what we also have is that the sort of, so if we just differentiate the sort of both sides with respect to x, then we get that sec squared theta, right? That's the derivative of tan theta, but obviously times d theta dx is going to be equal to, now let me do the derivative of this sort of right hand side, which is a bit annoying because the mod. You can't really take the derivative of mod x, or at least it's not as easy as it might seem, but you can split it up into sort of a portion where the mod x is going to be affected, where effectively x is positive, so the mods just go away, and you can split it into the sort of other region where x is negative, so you just have a sign in front, so you get minus x instead of x, right? Because that's how the absolute value of the mod is defined. It's going to be the mod of x equals x when x is positive or 0, and minus x when x is negative. So similarly here, if this is sort of, if the input here is negative, then all that's going to happen is we're going to get minus y squared minus x squared, right? But that's really all that happens. So it just kind of depends on whether y squared minus x squared is positive or whether it's negative. And so it just depends on the sign of y squared minus x squared. So if it's positive, then the mod will be removed. If it's negative, then there'll be a negative sign in front of the mod. Okay, so effectively then what we get is we get a, so the derivative with respect to x of a times the mod of y squared minus x squared is simply going to be a multiplied by the derivative of the mod of y squared minus x squared. A is just a constant. And this derivative here is just a multiplied by the sine of y squared minus x squared, right? And then multiplied by 2 y dy dx, right? That's the derivative of y squared with respect to x, minus 2x, right? That's the derivative of minus x squared with respect to x, right? So the sign here is just saying this is either going to be a plus or a minus. It's not like an actual number. It's just a plus or a minus. So it's a plus or it's a minus, depending on whether y squared minus x squared is positive. Because if it's negative, you get a negative sign from, you can remove the mods and just add a negative sign in front, right? So really that's all that sign thing is doing there. But then yeah, this is the actual differentiation part here, the 2y dy dx minus 2x. Okay. Now obviously though, this is, so then if we just sort of write this on the right hand side of what we have above, so sec squared theta d theta dx is simply going to be equal to, what's it? A multiplied by sine y squared by the sine of y squared minus x squared multiplied by 2y dy dx minus 2x. Now clearly, right, none of this is 0, by the way. None of this is 0. A isn't 0, and the sign is plus or minus 1. So if d theta dx is equal to 0, which is part of the question, is saying what happens if d theta dx is equal to 0, right? So if d theta dx is equal to 0, the left-hand side is equal to 0, and more importantly, the right-hand side therefore also has to be equal to 0, since these two things are equal, right? So this has to be equal to 0, right? So what we actually require, so we have, and just to like go back to the question as well, just to make sure that we're on the same page, we're showing that if d theta dx is equal to 0, then we need to show this sort of first thing here, that a times x squared plus y squared plus 2xy is equal to 0. That's what I'm trying to do right now. But effectively, because we know that d theta dx is equal to 0, the left-hand side here is equal to 0. None of this is 0, so this stuff over here has to be equal to 0, right? So we have that effectively what we have is that 2y dy dx, right, minus 2x is going to be equal to 0. And if we just arrange this, we're just going to rearrange it. We're going to get dy dx is simply equal to, or y multiplied by dy dx is simply equal to x, right? So we just put the 2x on one side and divide it by 2, right? So obviously we know what dy dx is, right? Because we figured it out from the first part of the question, right? We literally figured out earlier on. This is dy dx minus x plus ay divided by y plus ax. We need to use that. So this effectively implies that y multiplied by minus x plus ay divided by y plus ax is going to be equal to x. And then if we multiply both sides by y plus ax, all we're simply going to get is as follows. This just implies that minus y multiplied by x plus ay is equal to x multiplied by y plus ax, right? And then expanding and collecting, we're going to get minus minus ay squared. And then that there is going to be equal to xy add ax squared, okay? And so then if we just bring this all onto one side, we will see that we actually get the result we want, which is 0 is equal to 2xy add ax squared add ay squared, which we can just say that this obviously implies that a multiplied by x squared add y squared add 2xy is equal to 0. And this was actually just the required condition, right? So this is what we wanted. We wanted a times x squared plus y squared plus 2xy to be equal to 0. And that's what we ended up getting. So now we need to show that 1 plus a times x squared plus y squared plus 2xy is equal to 1. And actually for this, we can just expand the brackets. So let's just do that. So we have, what is it? 1 plus a, what was it? 1 plus a, so for that part, we have 1 plus a, I think it was, I'll just say what I think it is. X squared y squared add 2xy is equal to 1. Was that it? Was it 2xy? Yeah, 1 plus a times x squared plus y plus 2xy is equal to 1. Perfect. Okay, now let's just expand this. Let's just expand these brackets, right? So we have x squared add y squared add 2xy add ax squared add ay squared add 2axy is equal to 1. Now, obviously, if I shuffle things around here, what I'm going to get is x squared plus y squared add 2axy, right? And then add a lots of x squared plus y squared add 2xy is equal. We have to show, well, this is what we're trying to show. So I guess what I really should say is consider this, and then we need to show that that is actually equal to 1. And so effectively, by considering this, we have that it's just the same thing as x squared plus y squared plus 2axy, add a times x squared plus y squared plus 2xy. So in the previous part of the question, we just literally showed right above this is equal to 0. And from the first part of the question, we have this is equal to 1. Because effectively, we know that the coordinate xy satisfies x squared plus y squared plus 2axy because it's a point on the curve, right? And like effectively, the x and the y here correspond to x and y coordinates of a point on the curve, right? Because OP was effectively from the origin to a point on the curve. Okay. Okay, very good. And so therefore, what we have here is 1 plus 0, and this is just simply equal to 1 plus 0, which is simply 1. And so we've shown that it is indeed true that 1 plus a, so 1 plus a multiplied by x squared, 1 plus a multiplied by x squared plus y squared plus 2xy is indeed equal to 1. And that completes that part of the question. So for the final part of the question, we need to show that tan theta, which you already have up here, by the way, is a times the mod of y squared minus x squared, is equal to a over the square root of 1 minus a squared. Okay, so very interesting. So obviously from before, what we have is that tan theta is equal to a times the mod of y squared minus x squared. Okay. So, okay, how exactly are we going to go about this? Well, there are a couple pieces of information that we know that we could use to help us. So obviously, what we know is that a times x squared plus y squared, right, add 2xy is equal to 0. So if I effectively just labeled, if I just set s to be x squared minus x squared plus y squared, and I set p to be xy, then effectively what I get is that as plus 2p is equal to 0. So I can actually solve for p, and I get that p is equal to, and sorry, I didn't even realize it was zoomed in like this. So effectively what I get is that p here is just going to be equal to minus as over 2, right? And also, we know from sort of the equation of the curve that x squared plus y squared plus 2axy is equal to 1, right? And so if we just plug in, obviously this is our s, this is our p, so we know that s plus 2p is equal to 1, and so we can actually solve for our s. So obviously plugging in p as minus as over 2, you get s, well, it should be really minus as. S minus as is equal to 1, and then we just, oh no, sorry, because it'd be xy, 2, it should be 2ap here, so it should really be minus a squared s is equal to 1. And so this just obviously implies that s multiplied by 1 minus a squared is equal to 1, which obviously also implies that s is equal to 1 over 1 minus a squared, as required. Obviously, a is strictly between 0 and 1, so that denominator is not going to be 0. And then from there, we can figure out what p is by substituting that effectively back in, right? Because we have that p is equal to minus a over 2 times s. This is simply just going to be equal to minus a over 2 times 1 over 1 minus a squared, which is going to be equal to minus a divided by 2 times 1 minus a squared, right? And that's our value of p. Okay, well, you might think, why are those values of p and s important? Remember, p is xy and s is x squared plus y squared. But that's important because we can actually rewrite this sort of mod of y squared minus x squared. Remember here that effectively, note that we can write. So note, I go back up. Note that y squared minus x squared is actually equivalent to the following. So we could say it's y squared add x squared squared, and by the way, this should really be the square root of all of this. So this the square root of y squared add x squared squared minus 2xy all squared, right? And so what's going to happen is we're going to therefore get this is the square root, or really it should be the mod here. Note that the mod of y squared minus x squared is equal to the square root of all that. And then if you just calculate what that stuff is inside the square root, you're going to get y to the 4 add 2y squared x squared, and then obviously add x to the 4. Let me do my add x to the 4, and then obviously from there we minus 4 x squared y squared. And so when we actually sort of figure out what that is, we're going to get y to the 4 minus 2 x squared y squared add x to the 4, right? Which we can actually write as y squared minus x squared all squared. Y squared minus x squared all squared. That's y to the 4 minus 2x squared y squared add x to the 4. And obviously, therefore, we can see here that the mod of y squared minus x squared is indeed equal to the square root of y squared and x squared all squared minus 2xy all squared. But that's useful simply because now what we can do is we know what x squared and y squared are in terms of a, because we solved for them, right? That was our s and that was our p. So I can just literally plug them in. So I can get rid of all my x's and my y's immediately. So I know that my x squared plus y squared from before is simply just going to be equal to 1 over 1 minus a squared, right? And xy, that was equal to s, and our p was equal to xy, was equal to minus a over 2 times 1 minus a squared. Okay, so obviously we can just substitute all of that into our square root here and get the final answer. So this is just going to be equal to the square root of, notice that's s squared minus 4p squared, right? And so if we just calculate, what's that going to actually be? So it's going to be the square root of s squared, so that's going to be 1 over 1 minus a squared all squared minus 4 times p squared. Okay, very interesting. So obviously the 4 and sort of that minus there, they're going to cancel out. If we do, so obviously we calculate 4p, so we calculate p squared, we're going to get a squared over 4 times 1 minus a squared all squared. That's me, right? 1 minus a squared all squared. And when we multiply that by 4, this is p squared. We multiply that by 4, so that obviously implies that 4p squared is going to be equal to this 4 will cancel out, and that just gives you a squared divided by 1 minus a squared all squared, right? And so really effectively what you're going to get minus 4p squared is you're going to get minus a squared over 1 minus a squared all squared, right? And so you can combine this all up. This just gives you the square root. Sorry, I need to really just keep zooming out here. Just gives you the square root of 1 minus a squared divided by 1 minus a squared all squared. And that's just 1 minus a squared to the power of 1 divided by 1 minus a squared to the power of 2. So that just gives you the square root of 1 over 1 minus a squared, or otherwise the square root of 1 minus a squared to the power of minus 1, right? And effectively we can just say that this is equal to the square root of 1 divided by the square root of 1 minus a squared. The square root of 1 is just 1. So this entire thing is just equal to 1 divided by the square root of 1 minus a squared. And remember, this is just the whole rearrangement of the mod of y squared minus x squared. So the mod of y squared minus x squared is actually just the same as 1 over the square root of 1 minus a squared. And so from before, we obviously had that tan theta is equal to a multiplied by the mod of y squared minus x squared, right? And the mod of y squared minus x squared we just calculated is 1 over the square root of 1 minus a squared. So this entire thing is just a divided by the square root of 1 minus a squared. And that gives us the required result, that tan theta is simply equal to a divided by the square root of 1 minus a squared. Okay, there we go. Very, very, very interesting problem there.